I'm delighted to introduce our speaker. Dr. Kincho H is a professor of civil and environmental engineering at Stanford University. He's an alumnus of the University of Hawaii and received his bachelor's B.Sc in civil engineering and bachelor's of arts in mathematics from here in 1976, and his master's and Ph.D. in civil engineering from Carnegie Mellon in 79 and 81 respectively. He served as an assistant professor at Rensselaer Polytechnic Institute from 1982 to 88 and joined Stanford University in 1988. His research interests focus on computational information, science and engineering. His research has dealt with various aspects of high-performance computing, sensing, monitoring, and control of engineering systems, legal and engineering informatics, I want to hear about that, smart manufacturing, web services, cloud and internet computing. So the title for his talk is Data Science for Civil Infrastructure Monitoring. And his presentation will discuss the application of data science for civil infrastructure monitoring and discuss information on modeling of bridge structures to enable information interoperability and support structural modeling, engineering analysis, sensing and monitoring. He will describe the implementation of a cyberinfrastructure framework using NoSQL database and cloud computing platforms and provide selected examples of applying data analytics for structural monitoring applications. And this scalable infrastructure framework is demonstrated for the monitoring of bridges along the I-275 corridor located in the state of Michigan. So welcome, Dr. Lau. Really great to have you. The floor is yours.
Okay, so I'm going to share my screen and start my slides. So everybody see my screen okay? And also hear me all right, right? Okay, thank you. So once again, thank you for having me today. And I would like to share a little bit about one particular project that we have related to civil infrastructure monitoring. And we do bring in some data science type techniques into our project. So I would like to share with you today. So my name is Kincho H. I'm currently a professor of civil environmental engineering at Stanford University. I teach traditional structural engineering courses, but my research is mainly in the field of engineering informatics. So as Quinn mentioned earlier, I get my degree from University of Hawaii. In fact, I first went to Honolulu Community College before I can qualify to, I was able to qualify to enter University of Hawaii. And at the end, I do get a degree in both civil engineering and mathematics. And I was very much interested in computing. As I mentioned to a couple of people before, I worked in the computer centers, literally lived in the computer centers at Kalahau when I was an undergraduate student there. So a couple of professors recommended me to go to Carnegie Mellon. They told me there's a very good computing type school. So I went to Carnegie Mellon and I got my master's degree and Ph.D. and then stayed there for half a year for postdoc as well. And then I left Carnegie Mellon in 1982 and moving further east to upstate New York, taught at a place called Rensselaer Polytechnic Institute. There I learned a lot about computer graphics because they have a very good computer graphics center at the time. And then I had an opportunity to move to Stanford and also very much interested moving back to the West. So I joined them in 1988 and I have been there ever since. And my research interest is in the general area of computational science and engineering, basically how to apply computing, science and technology into engineering. Today we will talk about a little bit about related to civil engineering, but I also do work in the manufacturing system type problem as well and other type of domain in engineering. So what I would like to share with you today is the project that we instrumented a I-275 corridor in the state of Michigan near the Ann Arbor, University of Michigan, my collaborator there. And then we're looking at how to build a cyber physical system and how to monitoring the bridge and how to, and then looking at the type of data-driven analytics to help monitoring civil infrastructures. So that will be the basic outline of my presentations. So before I start, I always trying to do the acknowledgement before I forgot. So the project was funded by National Science Foundation a few years back, and also we get some funding from the Korean government as well through the collaboration with the professor in Korea. I would like to mention particularly the two students who actually work on the project. As I always say, professors like me talk a lot, but the students are the one really doing all the work. So the two students who work on it, one from Stanford, Dr. Jion, he's now working for VMware. And then the other student from University of Michigan, Ray Howe, he's now actually working for Facebook. And my collaborator, Professor Jerome Lynch, he is with University of Michigan. And also Professor Hong Zhang, he is with KAIST in Korea. So a quick disclaimer, anything I say here, stay here. That means that do not reflecting the views of the sponsor agency or my collaborator. And we have a few kind of computing system or methodology that we use in our research. I would like to also have a disclaimer that they are not necessarily the best product around, but this is fit to my research that we are doing. So that will answer the funding agency disclaimer clause. So you probably hear quite a bit recently about our civil infrastructures. This is the annual ASCE America infrastructure report card. And the civil infrastructure that including tunnel, bridges, roads, and airport and everything. Basically, right now, the score is a C-. Okay, that means that they are less than mediocre and almost poor. And now, of course, the politicians will always say they give a couple $1 trillion to fix our civil infrastructure. That remains to be seen. But how about bridges? The bridges that we have been getting a C-, C+, for the past almost 20, 30 years. And this past year, the grade they give is a C. So that is, bridges are kind of in the mediocre stage. So if you're looking at the conditions of bridges, okay, then what you see is the total bridges that managed by the Department of Transportation of different states, etc., is about 17,000 bridges, including some of them are overpasses. And there's about 280,000 is considered in good conditions. That means quite a large number of them are fair conditions, need some work on them. But we also had quite a large number of them actually structural divisions, say about 7.5% or more of our bridges are actually structural divisions, and we drive on it. So they all need to be worked on. And in fact, about 10% of the bridges have low end speed restrictions. So they tell you to slow down before you crossing the bridges, etc. So altogether, the report card estimated there's about $125 billion of backlog of bridge work that need to be done. And average it out, it need about $22.7 billion annually to rehabilitating our bridges in order for us to travel safely when we drive over the bridges. So in a way that our bridge conditions are not very good in general. But there are innovations that we do research, and there's a lot of innovations on the way, and some of them are already incorporated. So first of all, when you have a new bridge now, the design life is 75 years instead of the old days that they say 50 years. That has been originally 50 years. Okay. But note that a lot of our bridges is over 50 years old. I mean, in fact, more than 60% of the bridges are over 50 years old. We also started to using more high performance advanced material. Some of them are corrosion resistant, so that help a lot for the durability and also increasing the strength of the bridges as well. And also one of the key thing on repairing bridges that we're concerned about is traffic disruption, because it's affecting our economy when we shut down the bridges. So there are new modern construction technology like prefabrications. You do prefabrication and moving the members onto the bridge as you reconstructing it. And there's also technology called accelerated bridge construction that people also use using different type of technology. And another type of technology people now looking into is managing bridges is using non-destructive evaluation. So using infrared, using radar, and using all kind of drone, for example. You can actually have submersive drone to look at the scouring problem on the bridges, etc. So you can employ quite a bit of this new type of technologies into maintenance process and also inspection process. The type of technology that related to this talk is what they call living bridges. I mean, they actually written in the report card. It's called living bridges. What they really mean is that now we put sensors onto the bridges so we can continuously monitoring and provide feedback about the structural conditions. And that is the kind of technology that now many countries, including US and China and Europe, started to looking into putting sensors onto the bridge, embedding them onto the bridges, and hopefully that they will provide some meaningful information for us when we're maintaining and inspecting the bridges. So some of you might have heard about when the St. Antonio Fall Bridge, basically called Mississippi River Bridge in Minnesota, it collapsed in 2007. It was built in 1967. It collapsed 2007, and of course, right away they put in a replacement bridge. So every time you do a replacement of a bridge, it costs a lot of money. In this particular case, in 2008, it cost about $234 million. Okay, so this doesn't even including the downtime that people cannot travel in that particular corridor. So this is just a pure construction cost. But what they did put in is they put in about over 300 sensors put into the bridges, measuring corrosion, temperature changes, de-icing, and etc. Type of sensors that onto the bridge to monitoring the structural health, how good the bridge conditions is. Okay, and also of course the other thing is they collecting the data, hopefully to help future design of bridges as well, so they can monitoring the bridge that way. So when we don't maintain the bridge correctly, this thing happens. I mean, the bridge do collapse. Another case is the monitoring system being used is the fourth row bridge. Just to give you a couple of examples, that many bridges are being monitored, but this is another one that the reporting say in the new Civil Engineer magazine in August 2017. The bridge opened in 1964 and they having some problem in the early 2000s. Okay, because of the bridge over the rivers, they have corrosion problem. So So some of the pin support that you see on the top right started to crack and roasted out, corrosed out. So they have to repair, but during the repair that they want to open the breach as well. So how do they do that? They put sensors on. So they actually put in about 500 sensors, okay, and they do load tests and have a structural monitoring system. So basically the idea is I bracket out there. So the engineer basically say, we knew the bridge could safely carry the loads, okay? It's not because a computer simulation tell us they can carry the load, but it's because we load it 125 times and using the structural health monitoring system to measure them, and it is safe. So that giving the citizens some confidence using a structural monitoring system to say, hey, it's a safe bridge. Even though we are repairing it, it still be safe for you to travel. So those are the kind of advantage if we have a structural monitoring system. Okay. So of course, then like I said, they put in a lot of different type of sensors. I'm not going to describe each type of sensor, but they put in a lot of sensors. So the fourth row bridge at the end, they have about 800 sensors, and they collect about gigabit of data a day. Okay, so it's a lot of data that is being collected and you're collecting for analyzing it. Okay, and then when they put in a new bridge right next to it, the Queens Ferry Crossing Bridge, they put in over 2,000 sensors on. So since they say, oh, sensors are good for monitoring the bridge, so let us put more on it. And now this bridge, the sensing system collecting about 8 gigabit data per day. So what it really translate into, there is a lot of data. It's a lot of data that people are collecting. So there's some data issues. So I consider data science as two parts. One is how you manage the data. The other is how are you going to use the data? How you're applying the type of data analytics to utilizing the data. So there are two parts. One is how to managing the data. The other part is how to use data analytics to analyzing the data. Again, our purpose is to monitoring the structural health of the bridges. So we are focusing pretty much on the structural conditions of those bridges as our outcome. So the project that we have is funded by the Cyber Physical System of the National Science Foundation program. So we're looking at cyber physical system for infrastructure monitoring. So of course, there are multiple parts. One is the physical structures, which is the bridge. So we have a bridge structure, we have a physical structure. Then we put sensors on. So we have a sensor network and we do in situ monitoring when traffic going through. We measure the sensor data collecting from the bridge. And then we have collecting the data, then we'll build a information platform that including how we're going to managing the data. Can we use the cloud service to help us to organizing or managing the data, etc. And then what type of data analytics that we shall use so that we can actually confirming what's the conditions of the bridge. So that is the whole idea of a cyber physical system, integrating cyber infrastructure to supporting physical infrastructures. The test bed that we're dealing with is about 20 miles interstate 275. There's a corridor along the Michigan state. So what you see here is that we have the overall view on the test bed is we put a camera somewhere here, okay? And then the truck will go through and then we'll instrument sensors onto a bridge. So there's a telegraph road bridge. And then there's a Newburgh road bridge that we put sensors on. I will describe a little bit more in a minute. So this are measuring the response of the structure as the vehicle going through. And then we have another one, this is managing by the Michigan DOT, is what they call a weight in motion station that basically measuring the weight of the vehicle as it's going through. Okay, so there is a weight in motion station to measuring the weight of the vehicle going through, and then we have a camera system to capture as the vehicle also going through this particular corridor. Okay. So the basic overpass that typically people have is what they call slab on girder. So you put a girder underneath the bridge, you see, and then you put a slab on top and then try to tie them together. So we have, as I mentioned, there are two bridges that we're dealing with. So one of them we're monitoring a little bit more on our research is putting 60 sensors on it. The other one we only put 12 sensors. So it's not a lot of sensor, but we still can use quite a bit of this type of data that we can collect. So what type of sensor? We measure vibration. So we use accelerometers to measure vibrations of the structures. We're also using strain gauges to measure displacement deformation, but it's also in real time. So it's a time series data that we're collecting. And we're also using thermistor to measure the temperature in the locations. Okay, so that's what we would do. And the sampling rate's about 200 hertz for the accelerometers, 100 hertz for the strain gauges and the thermistor. And the data is acquired every 2 hours at the beginning for 1 minute and time durations. And I will show you later on, there's another strategy to minimizing the time duration to correcting the data for the type of information we're interested in. So we also have traffic video, as we said, we have a few cameras that we put up there. So give you a general picture how it look like. So this is like an overpass. So we have a base station. So we put in a base station. They are solar power. That means that we don't have to utilizing external battery system. So we solar power. So we have solar control the battery, and we have a transceiver. So this is all wireless. We're using a transceiver, using an LTE modem to transmit the data out. And we also have a little bit of compute engines. There's NVIDIA TX2, basically allow us to processing the data that we have on the system. And then the actual sensor is mounted underneath the bridge and along the girder. So this is the unit. Then basically the unit is a wireless unit. So this developed at the University of Michigan is called Narada wireless unit. So again, you have radio, extended radio, sending the data collected out to the base stations. And then we have the sensors that connecting to the Narada board. So we're collecting the accelerometer, acceleration data, strain gauges data, to the Narada board, and then we again is solar control. So this is a solar controlled battery that we have on the system. So it's a wireless system. It also have solar powered battery incorporated into it. So the weight in motion system is managed by the Michigan DOT. Okay, they basically put in underneath the pavement is in the middle lane is slow lane, and when the traffic going through, then you can measure the weight of the truck and also the speed of the truck as well. So the gross weight that collecting the axle weight, vehicle weight, and axle spacing. The truck have different spacing, and then also the speed of the truck. So there are many different type of information about the truck that they can measure. It's a very typical weight in motion that a lot of Department of Transportation use to measure the system. So there are some error when you're measuring them. So those are error we need to remember when we're doing monitoring system as well. So again, we also mount a camera on top. So there's a camera, they are solar panel operating. So again, using LTE antenna to send the data out. And we also have a little compute engines that also mounted with the to processing the camera images as we collecting them. So the frame rate is about 8 frames per second, and the connection is through the LTE modem. So the basic platform, cyber infrastructure platform that we put together is we gotta look at how to monitoring the data, how to define the data, so it's actually reflecting the bridge structures. We exploring how to use the cloud service. And we also want to try out a few computational services to see how we can assess the health of the bridge that we're dealing with. Okay, so to very quickly that talking about how to managing the data. First of all, we gotta come up with a data schema. So how to representing a bridge on on the freeway. So we follow standard. So there is a standard type work called Open BRIM. They first looking at how put together object-oriented data model to describe a bridge, particularly the geometric descriptions of the bridge, geometric description on the bridge. So you can look at it, it's almost like XML, but they call markup language. So they have objects, they have parameters, they have child objects that they can looking at, and they also have geometry information and definition representing it. But what happened to this type of schema? They primarily mostly interested in how to describe a bridge, the geometric information. But as an engineer, we need more than that. So we need to looking at how to representing an engineering model. So we built a data schema based on particular software called CSI Bridge. So we can actually directly tie back to the engineering model and simulations. Since we have sensor, we also use, prefer to use standard. So schema. So we use the standard schema called sensor ML. So we can representing different type of sensors and what kind of attributes, parameters for the sensors, then we can describe it. So the idea is that we want to building the data in a using open standard as much as possible, so we can have data interoperability among the standard and the tool, so they can communicating between engineering modeling, geometry of the model, and the sensor data all at once. So in a nutshell, then basically we linking the geometric model to what I call finite element model, basically is engineering simulations model. We also recording when a sensor put into a bridge, then we'll know exactly what sensors and what locations of that sensors are being put on the bridge. So we can capture all this information when we putting the data model and make sure they capture the information that we're interested in. So what type of database that we might want to pick? So in collecting this, a lot of different data, they are definitely unstructured data. A lot of them are time series data actually. So we decided to go for NoSQL, not only SQL type database system, because they have more flexible data schema. And as I mentioned that we want to be able to do some data, automated data conversion between the schema and the database system. And we also want to looking at cloud computing and see how they can be effectively help us to managing the data fast. That means we want to be able to get resources as quickly as possible. So the one that we have picked is called Cassandra Database, which is open source. So easier for us to play with them. And it's called the column family data storage. And what is nice about is we can also use it as a distributed database, data storage. And it's nicely mapping to the cloud environments that we can use. And it's quite flexible and very scalable. So we're using Cassandra, our base database. Now, again, you can pick many different type of database system, but this one is the one that we pick when we work on the project. So that's about a few years back. Okay. So as I mentioned that we can directly, using Cassandra database, we can directly mapping the XML format type of data directly into the NoSQL database schema. So that means we can write a script and easily creating the data schema that we representing the data that we use. Okay, so the bridge information we said before is object oriented. So we have child relationship, we have parent relationship. We're trying to model them as such. And we also want to make sure that they be able to representing engine entity. And we take advantage on the unstructured data. That means that we don't have to have every single entity have the same length. You can have different type of length per each attributes, and we can deal with that as well. So the Cassandra database seems to allow us to do quite a bit of type of modeling of the data itself. Okay, so now again, we integrating the data model with sensor entity. So this is just to illustrating we have some of those information. Okay, now, so as the truck going through, so we're collecting time series data. So for the sensor data, we can structure the data for period and then put it into an array. So very long arrays, and that allow us to do. And then we can put it into a column length, so we can have a many sensor data keep appending to a particular sensor during the period of time that we're collecting the data. For the traffic image, video image, and we're using block that as the way to capturing the collections of image onto as we capturing the images from the camera. So that's the way that we appending, concatenating the data, time series data into our database system. And we have timestamps. Make sure that we have the proper timestamp. We're collecting time series data. And we also put in a few things like clustering the key, using partitioning key to make sure that that we can retrieving the data as easy as possible. So that is when we have to deal with the distributed database when we're working on the cloud computing. So the other reason is Cassandra come with a very easy to use query language. They almost like SQL language that we can query the data. So we can query the data and then pass into the data analysis engines that we want. So again, we can collecting the sensor data per each station. We can, as the traffic going through, when the truck going through, we can collect the sensor data. We can then using the timestamp to retrieving the data as we wish. Okay, so we are also taking care of all the drift internally about the time clock drift, etc. That we do correcting some of those drift on our clock within the sensor itself. So that means that we now, as the traffic going through, we're collecting sensor data on the bridge. So we put into the cloud environments, so help us quite a bit. We don't have to installing a lot of resources directly using the cloud services. And so we use about 3 of them as a server nodes, and then you will try out 5 as a database nodes or for our backend database environments. Okay. So we build RESTful type services, basically put in data, getting out data. So we be able to getting the data in and out. So very quickly, why we're doing that? Because then now you can build web services relatively easy on your cell phone. You can, using your cell phone, look at a particular sensor, then you can look at the data. Or you can actually integrating with Google Map. So you put into a sensor locations and you can see exactly how the mapping to the Google Map and where the location of the sensor, etc. So we can build a lot of different web services that people can utilize in the data. So now I'm going to go into a little bit data analytics. I think most people are more interested in the data analytic part. So let's see what we using the sensor data. So I would like to emphasize that when we collecting the sensor data, we are trying to understand the behavior of the bridge, okay? And then trying to diagnose if what's wrong with some part of the bridge, why we see some phenomena that we don't like. Typically, people will do engine simulation inspection, but now we have sensor data, then how we can utilize them. So let me first give you a pure engineering example first before we get into some of the data analytics. So for example, that when we put in a snap on top of a girder, so sometimes, a lot of time, then we put in what they call a stuck, basically connecting the steel girder to the bridge stack. If you connect it fully, then you have what they call full composite actions. That means this guy here now, the entire thing working as a single unit to resist the load. If you don't tie it properly, okay, then you might have some frictions or no actions at all. Then you have what they call partial or no composite actions. That means the slab and the girder basically act independently when you have loading on top of the bridge. So in this particular overpass, the telegraph bridge, then what we have is in the main span, then we will have a much heavier girder, and we can foresee that is they also have full composite actions. And then the tail span is the 2N, okay? Then that is a lighter girder. It makes sense, a lighter girder because they're closer to the support, peer support. And then, but then they tends to ignoring the full composite actions when they design and putting things together. So what happened now, we have sensors. So we put sensor across the web of the girder. So putting sensors across the girder. So now you can collecting string data that is basically displacement data within the girder itself. Okay, how much elongations at the particular point. So when you're collecting this type of data, then you can plotting the strain diagram. Okay, so now when you're plotting the strain diagram, okay, then it will be something like as such. And what we'll be interested in is looking what they call the neutral axis. That means that's the point the strain is actually equal to 0. It's a 0 strain. That means no stress or strain on the girder when the traffic is going through. So that is actually the point that when you're looking at the end forces on the top part of the neutral axis and the bottom part, the total force on the bottom and the top, that the torque here, the torque creating from the top and the torque creating from the bottom are exactly the same. Okay, so that is with 0 moment or bending or stress at that point. Now, why are we interested at that particular point from the strain gauges data? Is that we're reflecting whether the member is fully composite or not necessarily fully composite. The reason is it's fully composite, as I mentioned. The whole girder acting as a piece. That means the variation of the strain or the stress is all the way from the bottom of the girder all the way to the deck is linearly varying. There's no discontinuity. But when you do not have composite action, particularly there is no interaction between the two, so you can see the girder at its own, while the slab is also acting at its own, okay? When you have partial composite, that means partially this is some string they're connecting together, but there's a big discontinuity. So the neutral axis will be moving from non-composite or fully composite is some locations on top, okay? Now, so what happened is the following. So when the traffic is going through, you measure the strain data. Now it's very data driven, measure the strain data. Then you're plotting the strain gauges as we see, then we find out what the neutral axis is. So what we find in the main deck, so in the main deck, then the capture the information lie around exactly the fully composited action part as a fully composite girder that we have. So that is how they designing this part. So you can see that what's designed is already taking into considerations on the fully composite action, make sure the pavement doesn't crack. But on the other hand, when you're looking at the tailspin, okay, you can see the neutral axis, okay, of the data doesn't really lie with the it lie within the fully composite actions and no actions. That means there's some partial actions, but it turns out that the designer kind of ignoring any composite actions in that part. What you see at the end is you see a lot of strains that are going on, then the pavement actually crack. So using the sensor data, then we can now translating back to the physical phenomenon to say why the pavement crack in certain part of the bridge, but not on the other part of the bridge. So using sensor data now, we can go back to analyzing the structural performance of the bridge stack. So now let's go to a little bit more data-driven simulations and other type of analysis that we're interested in. Say we can also calibrating the sensor data with the actual engineering model that we run on the computer. So we set up a engineering model, and we're going to look at the phenomenon and say, oh, what is the vibration frequency? How fast the oscillation when you have free vibration? So it turns out in the model that we calibrate, it find out the frequency is to be about 2.6 hertz, how fast it moves, okay, on free vibrations. Okay, usually if this is the good model, then we can run and truck around and find out what the response of the bridge. So that's how people then see how the simulation model can help us to inspecting or maintaining the bridges. But when we're looking at the data collecting, okay, then we get collecting time series data, particular acceleration data. And we can using this acceleration data to find out what the natural frequency of the bridge. And it turns out the natural frequency or the any model parameters of the bridge actually varying seasonally. This kind of makes sense. I mean, you know, in a place like Michigan, you can get relatively hot or you can get snowy day, you can relatively cold. It turns out the environmental effect through temperature and moisture that can affect the bridge response. So now we see these variations, okay? We can run through like Fourier transform on the acceleration data to find out those frequency, okay? So we say, well, is there any interesting relationship between the temperature or the natural frequency? So now you can plot it. Oh, we can plot the temperatures versus the natural frequency. Now again, in the numerical model, we can only get one. There's only a single model. You can only get one model frequency. But on the other hand, over the seasons, then we see variations on the natural frequency. It looked like something rather random and say, well, hey, is there any regressions that we might be able to see? So we don't know what that model is. So it looked like it's highly nonlinear. So we're using something called non-parametric type regressions that will give us the nice regression plot. Okay, we're using what they call Gaussian process regressions, and people in data analytics might have seen that before. And then now we also give you confidence interval. This here is about reporting 95% confidence interval. It's around the mean plus or minus 2 standard deviation. Okay, so we can directly using collecting the data, store it in the database, writing a simple Python script, pipe it into a Python-based machine learning package. In this case, is the package I think is scikit-learn. Okay, so we can using that and then finding the line, and then we can see, hey, there is some interesting relationship that we can see between the temperature and the natural frequency. In fact, it almost like a bilinear variations. If you started to see the regression, it looked like bilinear variations. Okay, so one thing is that now we trying to using the sensor data once again, now using a little bit of data analytics to kind of understanding how the structure is responding to some environmental effect. Then the other question is sensor fail quite often phenomenon. Sensor do get fail. So can we actually using now more sophisticated data analytic techniques to recovering the data? That means even when the sensor fail, but not all the sensor fail, then we may be using the good sensor data to predicting what would the sensor data supposed to be for those 40 sensors, okay? So, so this is called data recovery process, and when sensor mode. So what can we do? So we're collecting a lot of data. We're collecting a lot of data. So we know where we put the sensor. So there must be some spatial and temporal relationship correlating the sensor data as we collecting them. So we're utilizing them. So we take the sensor data for each of the sensor when they are when they're working properly along the same time frame. So we're going to learn from it. We're going to learn from that. And then now we're going to test it, okay, and see how good they are. So it's a basic machine learning process to utilizing supervised learning to do some of these things that we could do. So what we utilizing what we call bi-directional recurrent neural network. So we take a large number of data points, say 100,000 data points. Okay, we collect so many, we can always find a chunk that are good. So we could collect 100,000 data points. Then we feed forward and feedback work. And then we also have recurrent within each neuron itself. So we're utilizing this technology using bidirectional recurrent neural network as the way to recovering the data that we lost because of faulty sensors. So it turns out we work quite well. So we compare with the principal components or feed-forward neural network, or even just the recurrent neural network itself. We find that bidirectional recurrent neural network seems to mapping the data quite well. So we can see the error is almost minimum when we can learn from the past data. So what are we going to use it for? We use it for when certain sensors, we put a lot of sensor on, but some of the sensor might be malfunctioned at a particular time frame actually happens. Okay, so it is no longer a testing, but basically it's a scoring part of the process. So we're utilizing what we learned. Now we don't necessarily need to utilize all the data, or we can using one side of the data on one part to discover the sensor loss, data loss, and then using the other side and recover the sensor data loss on a particular sensor. In fact, we could do that. We learned, and then we, from previous data set, and then now for the sensor that we lost the data, now we recover those data set that we may be interested to use. Okay. For example, suppose that I'm interested to get the modal frequency, the natural frequency, or want to get back the mode shape, the vibration shape of the entire bridge, then we need all the sensor node information. So since we recover the data for those sensor nodes, then we can directly apply to get the frequency and then get back the mode shape. Compared to the other data set fully collecting, then we see the data are actually reconstructed very well and provide us a very good estimations. Then we can directly reusing some of this data in that particular time period for other purposes as if we interested of using them. So let us move a little bit more sophisticated use of machine learning a little bit, particularly using computer vision. So as we said before, we want to monitor an entire corridor. So what happened is when the truck is going through the corridor, it will going through the bridge with the structural health monitoring system, okay? And then it will eventually get into the weight in motion that you can measure the truck weight. We'd like to emphasize once again, when you're looking at the bridge, we have the structural monitoring system that is only collecting the response of the truck. It doesn't really know what the truck weight is and what the speed of the truck is, okay? So, but then we have this information on the weight in motion stations. Now we can measure the truck weight, okay? But then we have to find out, is it a truck? First of all, okay, do we know that it's a truck? But then when you're capturing with the other camera, are we capturing the same truck? Are we capturing the same truck? So when we're capturing the same truck, then we know that we have the right measurement. The second purpose of doing this is we're doing triggering strategy because all we're interested is truck. So we want to be able to capture the truck, say, oh, this is a truck. So now you can say, send a signal to the monitoring system and the weight system to say, turn them on. So now you can saving the battery so you don't have to constantly operating. So you only trigger them and then collect the data you really want to do, which is the truck, because truck has the most demands on the bridges. So we only interested in the truck as they go through the corridor. So we need to do that. So computer vision now is so powerful that we can now actually do a lot of these things. So the first thing we want to be able to capture, is it a truck? So we have a truck detection problem. We want to capture the same truck as it going through. So that is now become a identification of the truck as they going through the bridges and the weight in motions. Okay, so we started to do machine learning and collecting the data set. So of course, like most of people do, they're using the ImageNet to using the original model training and capturing the pre-trained model. And then we started capturing the online images from online, and we also collecting data directly that we from our camera through the I-275 corridor, and then we started to labeling some of this data. So we start labeling some of this, though we have altogether capturing 4,400 training data and test data. We're using 1,200, and altogether we basically 56, 70 instances, and we collecting all together utilizing 3,500 images. But we're using 3 classes just to make sure we distinguish them, and we have truck, pickups, and car. Okay, so we're collecting data, label a few of them, not all of the data, just collecting a few, and then we label them, and then we run through it. We want something real time. We want to trigger, so it means that we gotta have a real-time triggering system. So say, here's a truck. So we're using what they call YOLO Tiny, which is extremely fast, but we also find it to be quite accurate. So in this particular scenario, we're using the YOLO V3 Tiny as a triggering. So we learned we trigger. So you're looking at the triggering time is really, really small. Okay, you only have 3.2 milliseconds to find the image and say this is a truck, and then you pass it along to the other sensor to trigger them on. For the other stations, they all we care about detecting a truck and then do an analysis. So we want to have even better accuracy. So we're using YOLO V3 as that can run offline to recognizing truck as they go through. So this is the first step, is identify the truck at each station. It is a truck as they're going through. Then the second thing that we want to do is say, am I getting the same truck? Am I getting the same truck? So we want to be able to identify the same truck. So that means that when we capture a truck, we want to creating a feature vectors. We want to creating a feature vector describing what a truck is. So what we were using a triplet architectures that this company use for doing similarity analysis. So we basically say negative, positive, and the anchor image and training the triplet. And it turns out that this architecture with a basic CNN-based encoder to give us really good precision, and we call it F1. So this is kind of give us a very good confidence that when we identify a truck, that this is the right truck. Now, don't get me wrong. They are false positive. Okay, they are false positive, but they are not a lot. Okay, so that means that we are now kind of confident most of the data that we're collecting from the triggering system with the truck is actually most of them are the same truck as they're going through the entire corridor. So the first thing is that we see when we can capturing the same truck, then we can now going back to say, hey, when you're triggering to say 70 seconds later, or up to 170 seconds to trigger the first sensor on the bridge to turn on, the second bridge to turn on about 330 seconds later, and then 630 seconds to turn on the camera on the rim system. Is it good enough? So we can go back to looking the information from the machine learning technology that we have to basically telling us is the range of time that we're collecting those data capturing by the period data that we are on our triggering system. It turns out that is actually mapping quite well. Otherwise, we can also go back to re-instrument the system as well. So now we say, well, we identify the same truck. Then what the usefulness is, now we can linking exactly the same truck with the sensor data, okay, on the two bridges with the actual loading. They actually we know this is the truck, this is the loading now causing the bridge, okay? So combining them, then we can do meaningful engineering analysis with them, okay? So one of the example, okay, this is the just to give you an idea how we're utilizing it. We need to rating the bridge. That means that, hey, how good the bridge is, okay? That is what is the remaining load capacity, okay, after the weight of the bridge itself. That means the light load versus the maximum dynamic light flow that there's a vehicle going through the truck. This number has to be greater than 1.0. Otherwise, then the bridge is no good. Okay. So in calculating them, there is some parameters called dynamic load allowance. This is the static light flow, and then your dynamic amplifications on the static loading of the truck. That will give you amplifications of the light flow, amplifications of the light flow on the bridge. So now we can looking at that number, since now we're measuring them. So now we're measuring them. So we can directly utilizing the measurement, okay, going through the machine learning process, identify the same truck. Then now as the truck going through, then now we can say what the dynamic allowance factor actually is. So now, as I mentioned, we know the same truck going through. So we have one of the bridge, then this is the sensor data. So we can take the peak that turned out to be the maximum dynamic response of that particular truck, okay? And then we can say, well, when we're doing some filtering, using some basic filtering, okay, then we can come up with the static value. So we can come up the maximum static value. The dynamic load allowance is based on the differences between the maximum dynamic response, subtracting the maximum static response divided by the light flow response. So that basically is the dynamic load allowance. Now, we are now using the data that we can collecting of a same truck going through the entire corridor, identify using computer vision techniques as we've gone through, as the way to calculating this dynamic load allowance, okay? So in the code, they're primarily interested in the truck on 72 kip. So now we are analyzing all the trucks. So we're looking at 72 kips and also taking into considerations on the error that the way in motion might have. So that's about plus or minus 15%. So now we can calculate what is the dynamic load allowance versus what is the allowable factor that we have to say that now you can measure whether the bridge is more or less safe or not safe. So now it's purely data driven. In the code, most of the techniques are based on empirical data. Okay, just basically, oh, this is a simple design, you're just using this number. Or you're using finite element model, the engineering models that we saw earlier, analyzing those models, and then get the information out. What we are now saying, since we have sensor data, maybe we can now start to think about using more data-driven techniques based on the real-life data that we're collecting, reflecting the real conditions of the bridge, okay? As opposed to what the model most of the time is based on what you design, not necessarily the current conditions of the bridge, okay? So those are the kind of data-driven techniques that now we can using data analytics that we talk about. So, so I know I'm running out of time, so I just summarize. So what we did in this project is to build a cyber physical system. We put sensor on the bridge, okay? And we built a back-end data management system. And these are just a few examples that I just showed you. We have a lot more examples, but this is just a few examples. The key thing is we want to be able to translating back to the engineering language that people can utilizing the information that we collecting on the sensors and analyzing them and reflecting to the engineers. So again, why data-driven approach is useful? Because we are measuring the real in-situ conditions of the bridge, not something that you put in a simulation model. Very likely will be based on the original design. Okay, so we are now in real time be collecting data. We can analyzing the data. As you analyzing the data in real time, that means now you can identify problem before that causing the dangerous situations. And you can actually utilizing the data now to more intelligently arranging maintenance and inspection scheduling. So that means now you might be able to stretch a little bit more resources according to the conditions of the structures. As you keep monitoring the bridges, you know what is good and not good. That means you are, in general, enhancing the public safety. Okay. Now, again, sensors are not expensive. they are only a tiny expenditure of the entire bridge that you put together. So it may not be maybe a inexpensive way to help us to monitoring a lot of the bridges. Some of them are old, to see how far we can stretch it to. So in summary, there are many opportunities to incorporating modern data science, data analytics into engineering practice. So again, this is a very quick overview. So I didn't drill into a lot of analytic techniques because I know this data science institute, some of the methodology I mentioned, you probably know better than I am. But we bring together both data management, instrumentations, and all the way to data intake, application data intake to this problem. So thank you for inviting me. I really appreciate it. I hope that I may be talking too fast or whatever, but hopefully there's some discussions and comments, and feel free to ask any questions. Thank you very much.
Well, thank you so much. Wow, such a fascinating seminar on, I mean, I had known about cyber physical systems before, but I'd never really heard this whole story on how you would instrument a bridge and detect trucks and all that. That was fascinating. I'm sure, excuse me, I'm sure we have some questions from folks in the audience. You could either just go ahead and ask your question or type it into the chat.
Feel free to ask the questions.
Yeah, just feel free to ask a question. I don't see one yet, but I'll start out. I'm just curious, Dr. Law, whether you see some of the new federal kind of funding priorities about infrastructure. You know, it seems infrastructure is the word of the day now. Just curious about your feedback on that, and whether you think that's really going to turn into all of our bridges should work and all of our roads should be, and maybe they'll patch a few potholes here in Hawaii too while they're at it.
I believe it when I see it, the money. Every single president, when they campaign, they always talk about infrastructures, all the way from, you know, back in the old day, Clintons and Bush, Obama, Trump. In fact, Trump is an interesting example. When he campaigned, he's going to put in $2 trillion into the infrastructures. What's interesting is I actually gave a seminar in China right after he announced it. I mean, he won the campaign and then he announced that he's going to put in $2 trillion. So I gave a seminar in a university in China, and then the students start raising their hands. It will be so many jobs for civil engineers in the United States. $2 trillion. I mean, there's a lot of jobs, right? And did we see it? No, we didn't see anything, right? So now, you know, President Biden also announced it, infrastructure bill, right? So I don't know how it will go. So, I mean, I wish that they will come through. In fact, I would like them to put in a little more new technology into it. I mean, like big, you know, the better internet or from better grid and all the way to energy grid, all the way to the infrastructures, have a lot of money into it. But no matter how you're looking at it, even the dollars they put in, just talking about the roads and bridges, you're talking about the figures that I just showed at the beginning. What they put it in is still not sufficient. But on the other hand, it helps, right? I mean, anything helps. But our infrastructure being ignored for so long, some of the bridges that you're going through actually almost in the state of collapse. I mean, they actually have low restriction signs out there. If you're over certain, you know, tons, you shouldn't be going through, etc. So I thought Hawaii is doing much better than we do in the mainland. So I don't know, but but pothole. I mean, in the East Coast and particularly the Northeast, pothole. I mean, California, we have tons of potholes. So I like I said, I believe it when I see it. So I hope that it will come through this time. I mean, but so far for the last 5, 6 presidents, I haven't. Everyone talk about when they campaign, but once they become president, then for whatever reasons,
Yeah.
doesn't happen. Didn't happen. I mean, they're Republican and Democrat, by the way. I mean, I'm not trying to mention, just
Yeah.
Republican or Democrat. They, Bush, Clinton, Obama, Trump, so.
Yeah.
So.
Well, great. Well, we sure know that these things don't repair themselves. We do have a question from Dan Smith. Any buildings at Stanford? Are any buildings at Stanford instrumented?
We have some, but not in the infrastructure side. One professor actually monitoring airflow in our building, the Yang and Yamasaki energy environmental building. So one professor is actually doing some airflow type sensing. They interested in clean air or airflow type things. So there's some of them are instrumented. Okay. But Salesforce has a sensor system in the Salesforce building, by the way.
Oh.
So there's some in 2 buildings now. Okay. So building is a little bit more tricky because they are private buildings. Most of them are private. So you do need the owners to willing to spend extra money. The other negative side, I don't mind to mention it, even though it's recorded, is when you're putting sensors on the building, you as a private, you might increasing your liability about what you have. Because if you don't know it, you can declare ignorance when there's something happened. When you know it and you don't do anything about it, or you don't really do it right away, then you could have liability issues. So for private industry in this country, the legal system not necessarily favor. You catch what I'm saying? Now for public system is the other story because you can, you do want to have public safety. But private, we were told, many years ago, we tried to contact a few building owners, and there's something they mentioned to us. They say, we don't know, then you can declare ignorance. If you do know and you don't do it right away, then you can cut into some legal issues. Okay, so buildings is a little bit more tricky. But in China, there's a lot of buildings being instrumented, same as a lot of other countries. But again, infrastructure is different. So more and more infrastructure now, people willing to do monitoring. I hope I answered your questions.
Yeah, you certainly did. Do we have any others from anyone in the audience that would like to ask a question? Don't be shy.
Yes, Paul. Okay, so assuming that the instrumentation bridges, and, for example, are used for routine monitoring and for the either for scheduling maintenance or for actually for an alert system when there's something of concern. And do we know anything about the so the false positives and false negative characteristics of these monitoring systems?
One of the reasons why we're interested in some of the sensor data recovery type of algorithms is actually trying to go back to cross-validating among themselves. So I illustrating when the sensor go down and then you say, well, it's the sensor data, you can reconstructing them. But you can actually apply it the other way. Can I using other sensor data to cross-checking the sensor themselves to kind of see if they outlines based on the data set that you collecting before. So that is one possibility to make sure, first of all, the sensor data is kind of good first. Of course, I mean, you're going to like any system, they're going to have false positive and all, you know, different issues. But what we trying to say, we're not replacing engineering practice. We're just giving them a lot more real-time information. So hopeful that will help them to do a better job in the inspection maintaining process.
Right, so you don't see this right now as a way of scheduling routine maintenance, for example?
You could say, you know, you can ask a question if you have confidence on the sensing system for, you know, time, then you say, well, can we stretch it for 6 more months?
Yeah, exactly.
So possible. I mean, that's something possible to do.
Or, you know, or which particular girders need more attention, so forth.
Exactly. But I mean, but I'm not going to say, well, you shouldn't. I mean, right now, the typical cycle is about 2 years that you have the inspections. Even though it's perfectly okay, you do 2 years. It might be, you know, you might need it more earlier, or you might need it slightly, you know, you can extend it a little bit later. So in a data-driven way, if you have enough confidence, I mean, you need to run the sensors, et cetera, for a little bit longer. Then you have much more confidence, then maybe you can extend it to a newer bridge, maybe 3 years. Saying you can stretch a little bit. The older bridge, then you worry a little bit more, but based on the sensor data, maybe instead of a year, maybe a year and a half. I mean, I wouldn't say that you don't want to go back to inspect them at all. I mean, that's just not what we're saying, but it's just that the data might be able to give you, and also, I mean, even when you have inspector over there, by the way, the adjustment usually is very subjective. Now, for example, the Mississippi River Bridge, they inspect every year because they knew there were a problem. They actually inspecting every single year. Okay, the thing is still have problem. Okay, so the idea is that we have a sensor, there may be some deformations that the inspector missing, or some other things that they're missing that may be able to see from the sensor system. So in addition to the traditional inspection process. So that's what we're trying to say. Okay. Just like autonomous vehicle, I mean, are we so confident now you allow the vehicles to run? It's probably not for a little while yet, right? So,
Thank you.
But why not using sensor? I mean, it's not that expensive, really. The base station may be, but still, I mean, relative to the bridge constructions, if you need it, is a tiny fraction. So, of course, my interest is putting more and more interesting technology on bridges, then we can do better things. So. And I would like to emphasize, I mean, a lot of techniques that we use that we're not, you know, we're not as an engineer, we're not trying to do research in data science per se, be very clear on that. We're utilizing what people have done in computer vision, computer science, and we see the potential applications, and then we bring them in. And then we may treat a little bit or building something on top of it, or amend it a little bit, then we can apply into our engineering world. We're not necessarily using the most sophisticated machine learning technology, but we're trying to use the one that's going through our experience that works. So that's what we're trying to do. So I don't want to say that we are data scientists. I'm not a data scientist, I'm engineers, but I happen to like to use data science techniques to apply to engineering problems. So, because a lot of computer scientists don't like me to say I'm using computer science. Basically say I'm using computer science techniques to help me to solve my engineering problem. So, yeah. No, I think a lot of computer science. I mean, you know, convolutional neural net is, I mean, really gigantic breakthrough that we can use it in engineering. I mean, almost any engineering problem. I have many more applications that I can talk about how we're using CNN. I mean, you know, one of the projects that we have with the people at UC Berkeley at the simulation center is giving Google Street View can we identify what they call soft story. That means the first floor is kind of weaker story. Then subject to earthquake, they are likely to have damages. So we just using Google Street View, capture the buildings and then running through machine learning and say, oh, these are the buildings that at least on the surface, they look like they are called soft story. So maybe now facilitating the people going there to inspect those buildings. Now, we don't know what's inside. Maybe they already retrofitted it. So they have to cross-check their own database. But at least that on the vision-wise, then we see on the outside, that doesn't look like a building that you might want to pay attention to, example as such. So that can actually helping a lot of inspection process, right? I mean, if you know the building look good, then why you won't send someone over there? So we borrow a lot of techniques from computer science in machine learning to help us to understand a lot of those. So we do reinforcement learning on robotics, for example, to find pathfinding using reinforcement learning. So there's a lot of amazing techniques that data scientists like you guys develop that we can borrow to in engineering. So all that we need is to train engineers to will understand data science and willing to put them back to engineering. I mean, that's what we need to do, right? So.
Well, with that, we'll close down our seminar for today and wish everybody a wonderful weekend and happy Aloha Friday to everyone.
Yeah, Aloha Friday, yeah.
All right.
Thank you. Thank you so much for having me. So.